Last time, in making things up, we watched GANs, VAEs, and diffusion conjure images out of pure noise, and every one of them learned by following a gradient downhill. But here's the thing, we've called model.fit for 24 episodes and never once asked how it computes those gradients. Today, we open the box. This is the train stage again, but the custom bare metal version, meet tf.gradient tape, the autodiff engine sitting underneath every fit you've ever run. Start with what we've been hiding. When you call fit, three things happen on every batch. A forward pass computes the loss, a backward pass computes the gradient of that loss with respect to every weight, and the optimizer nudges the weights. We've only ever seen the outside of that loop. Today we crack it open and look at the gear in the middle, the backward pass. How does TensorFlow get those gradients? Not by hand deriving calculus and not by nudging numbers and measuring. That's too slow and too noisy. It uses automatic differentiation. As your code runs forward, TensorFlow secretly records every operation onto a tape. Then it replays that tape backward, applying the chain rule at each step. The answer it gets is exact, accurate to the last decimal, not an approximation. The tape is a real object, TF gradient tape. Inside its width block, TF watches every trainable variable you touch and remembers the math. Step outside the block, call tape gradient target sources, and it hands you the derivative. It's that literal. The tape watches, you ask, it answers. Let's prove it isn't magic. Take the simplest function you remember from school, y equals x cubed. Calculus says the slope is 3x squared. So at x equals 2, the slope should be 12. We let the tape watch x, compute x cubed, and ask for the gradient. It returns 12.0. Try every point along the curve. The tape traces out 3x squared exactly. Autodiff agrees with calculus everywhere. Now nest two tapes inside each other. The inner tape computes the first derivative. The outer tape differentiates that. Out comes the second derivative, the curvature. This is how you reach things plain fit never gives you. Newton's method, physics with acceleration, optimization that uses curvature. One derivative is a slope, two derivatives is how the slope itself is changing. And gradients aren't the whole story. TensorFlow ships tf.linalg, a full linear algebra toolbox, matrix solve, least squares, Cholesky, eigenvalues, SVD. Machine learning is just one customer here. Fit a curve to lab data, solve a stiff physical system, decompose a covariance matrix. Same engine, same GPU, no neural network required. This is the scientific computing in scientific computing. Put it together and you can take the wheel from fit entirely. By subclassing a Keras model and overriding one method, train step, you write the forward pass, the tape, the gradient, and the optimizer step yourself, while still keeping compile, fit, callbacks, and metrics. The trick is to track your own metrics explicitly. A loss tracker and a metric object you update by hand, and expose them through a metrics property so fit can reset and report them. Full control when the defaults don't fit, custom losses, two optimizers, gradient surgery, your loop, Keras's conveniences. One catch, a handwritten Python loop is slow, so you wrap it in at tf.function and TensorFlow traces it once into a static graph, then runs that graph at C++ speed for every step after. Same code, often 2 to 3 times faster. The science is settled, the gradients are exact, and the loop is fast. Next, we package the model up and ship it. Serving. Here's 25 autodiff or .py, 3 pages. We'll go top to bottom. A sanity check that x cubed differentiates to 12. Nested tapes for a second derivative. A physics fit driven by tf.linalg. A custom train step model. And finally, the art tf function speed up. No fit until the very end. And even then, it's our loop underneath. First, the sanity check. We make x a variable set to 2.0, open a gradient tape, compute y all on x3, and ask tape.gradient_yx. TensorFlow returns 12.0 and 3 times 2 squared is 12. Autodiff matches the textbook. We print both side by side so there's no hand waving. Now curvature. Two nested tapes. The outer one watches while the inner one computes the first derivative dx. Then the outer tape differentiates that to get d2y dx2. For x cubed, the first derivative is 3x squared and the second is 6x. So at x equals 2, we expect 12 and 12. Both print exactly. Nested tapes, second derivative, done. Here is the science. We have noisy measurements of a damped oscillation and we want two physical parameters, stiffness K and damping. We build the design matrix A, stack the observations in B, and call tf.linalg.lstsq to solve the least squares system in one shot. It returns K near 3.14, damping near 0.21, and a residual down at the noise floor, about 4 times 10 to the minus 4. No gradient descent, no epochs, a direct linear solve. Now the custom training loop the Keras way. We subclass Keras.model and override train step. We also create two metric objects up front, a loss tracker and a mean absolute error metric, and expose them through a metrics property so Keras can reset them each epoch. Inside train step, open a tape, run the forward pass self xb, compute the loss with self.computeLoss, then tape gradient against self, trainable variables and self-bound optimizer, apply gradients. We update our two trackers by hand and return their results as a dict. This is exactly what StockFit does internally. We've just written it out in the open. We wire it up like any model, instantiate, compile with an optimizer and a loss, then call fit. Because we overrode train step, every batch now runs our code. But the progress bar, the metric logging, the callbacks all still work. Watch the loss fall from about 9 down past 1/10 over 8 epochs. Our handwritten step is really learning. That's the payoff. Total control over the gradient step, zero loss of Keras conveniences. Last, speed. We write the same step as a plain Python function, then decorate a copy with @tf function. We time 1000 iterations of each, then print the ratio. The eager version runs Python on every step. The compiled version traces the graph once and replays it. Same gradients out. The timer reads about 2.6 times faster. That's the difference between an interpreted loop and a compiled graph. So that's the engine room. The tape records and replays to give exact gradients. Nested tapes give curvature. tf.linalg solves the science directly. A custom train step hands you the wheel, and a tf.function makes it fly. Every fit you'll ever call runs this exact machinery. The model's done and the math is settled. So next time we package it up and put it in production, saved model, TensorFlow serving and TensorFlow.js, shipping it.